Welcome to Coffee Break, the live stream series brought to you by Microchip Technology, where our mission is to educate, entertain, and empower you to innovate in your designs. I'm your host, Dana Curtis, and you are watching the last episode of Season 13. As always, we're here to dive into the fascinating world of embedded control technologies, integrated circuits, and all things smart, connected, and secure, in about the time it takes to enjoy a fresh cup of coffee. For those of you joining us for the first time, welcome. Coffee Break is a live broadcast, and we encourage audience participation. Before I introduce our special guest, let's take it over to Aliyah Fahout for some housekeeping items. Aliyah, what do you have for us?
Thanks, Dana, and hi, everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and we invite you to participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after this broadcast. If you're with us on YouTube today, make sure to subscribe to our channel and click the bell so you know when we're live and when our next episode is. If you're with us on LinkedIn, subscribe to the event to get all the information related to this episode. Back to you, Dana.
Thank you, Aliyah. Today we have a very special guest joining us. Pramit Nandi is a product marketing manager of the Digital Signal Control business unit here at Microchip. Welcome.
Thank you.
Nice to have you here. You're joining us today to talk about the dsPIC33A digital signal controller, and we're going to talk about real-time control in embedded applications.
Yes.
So, we have our coffee ready. Let's start with the obvious question. What are digital signal controllers, and what are some applications that might require real-time control?
Thank you, Dana. I'm really excited to be here. So to answer your question, so digital signal controllers are basically a hybrid between a digital signal processor and a microcontroller.
Okay.
So you get the best of the both worlds because you get the computational power of the digital signal processor so that you can do math very quickly. Mm-hmm. And then you have the simplicity of MCU to adapt it in an embedded system application. So it's a hybrid.
Right down the middle, yeah.
Exactly. So it is very useful in real-time control applications like motor control, where you use field-oriented control for achieving higher levels of efficiency, low noise motor control. Then there's a lot of digital power conversion applications in cloud power, data center, even EV infrastructure. And there's sensor interfacing. You're always talking to the analog world, so you have to interface with that and compute what you need to do and then talk to the peripherals. So yeah, lots and lots of application in different market segments.
So let's talk about those markets and applications. Mm-hmm. Where do you think the dsPIC33A really excels?
Well, that's a very good question. So in dsPIC33 series has been around in the Microchip for over 2 decades now. Mm-hmm. We have lots of application in automotive, for example, motor control, because there are anywhere between 40 to 100 motors in modern cars, whether it's an internal combustion engine and electric vehicle, of course, has even more. Mm-hmm. So it could be in the form of pumps for oil pump or coolant pump, fans, radiator fans, or any cooling fan for the battery. And then there's a lot of sensors as well, whether it's pressure sensor, temperature sensor, current sensor. All those applications require a microcontroller.
Right, that's before you even get into the cabin of the car, right?
Exactly, exactly. And then there's backlighting. Mm-hmm. Nowadays, the backlighting has become very fancy. Yep. Lots of animation there.
Ambient lighting. Yep.
Yeah, so that requires real-time control. So dsPIC DSC shine there. And for industrial, again, sensors, pressure, temp level, flow, temperature, current, all those kind of things. There's lots of application there. Of course, the motor control. In case of industrial, of course, along with the brushless DC motor, you also get lots and lots of AC induction motors. So dsPIC DSCs help there, especially with the drives for those motors. And if you go to the sustainability solution side of things, lots of application related to e-mobility, like e-scooter, e-bike, e-motorcycle, and in southern Asian countries, you have the three-wheelers. Mm-hmm. They have also migrating to electric versions.
A lot of it seems to be mobilized to electric vehicles, yeah.
And they're called tuk-tuks. Yeah. And then there's also appliances, right? Everyone is trying to achieve higher levels of efficiency, whether it's HVAC units or your any appliance that you use at your home. And then there's renewable energy resource-related applications like power conversion for solar inverters, right? Mm-hmm. And then there's lots of application on the digital power conversion front, like cloud power, data centers, especially with the advent of AI.
Yep.
the number of power supplies required is quadrupled
Yeah,
or
data
even more.
centers are growing like a weed. Yeah.
Yes, so whether it's the power factor correction side or DC-DC converter side, the same thing is needed for EV infrastructure as well. Then there's wireless power for charging your phone. So lots and lots of applications for dsPIC DSCs.
So what's driving the need for this increased performance? Is it complexity or is it something else?
Well, it's a kind of a mix of things. So it's primarily, I would say, driven by 4 trends in embedded systems. So first trend that we see is everyone is trying to achieve higher levels of efficiency, right? So
Everybody wants to do more with less, right?
Yep, exactly. So people are trying to achieve that efficiency either to meet with some certain standards or meet some government norms. So for achieving that, you need better hardware, better end equipment, and also to control them, you have to use more complex algorithms. So for running those complex algorithms, what do you need? You need more computation power. So you need higher performance. The other trend that we see is one controller performing multiple functions. This is pretty much done to optimize the control loop, have a better performance, and also to simplify the system architectures.
We're talking about space and cost, right?
Yes, because you have lots of things coming in together, so you can definitely have some board space savings too. So this is a trend that we see, for an example, in automotive electric vehicle. The thermal management system, which is in charge of cooling the battery, the motor that's running, and then also the cabin temperature. All those things are done by one single controller. So as a result, it's running so many things, you need higher performance. Then the third trend that we are seeing is pretty much the increasing demand for safety and security across various segments. You need to run additional safety or security library on top of the real-time application that the MCU is performing. So guess what it's going to do? You need more performance. And last but not least is the increased software complexities, primarily driven by model-based design because people want to simulate things before they actually design the stuff. So that's where the abstraction layer complexity increases, additional abstraction layer. And then there's also a complex ecosystem. If you look at automotive, there's AutoSAR, and then there's MCAL drivers. All those things add additional layers of abstraction.
The more features we pack in, the more software that's going to drive it.
Exactly. And for that, you need more performance. Yeah.
So are these market trends the primary driver for development of a 32-bit solution?
Yes, definitely. But then there are definitely other factors. For example, if you look at the graph here, so for dsPIC DSC family, which have been around for over 2 decades at Microchip, we have been making gradual improvements in the core, from switching from 30 megahertz, 20, 40, 70, and going up to 100 megahertz in the 4th generation.
Yeah, it seems like a bit of a linear progression until you get to the
exactly
to the A.
And then we also made gradual progression and improvements in the peripherals too. But if you look at the A core, you see that it's operating at double the
dramatic
clock
increase.
frequency. Yeah, and on top of that, the big change is that it's 32-bit architecture as opposed to the 16-bit architecture of the previous one, and it also has double precision floating point unit. And that's not enough. We also significantly improved these peripherals, higher speed peripherals and new peripherals for application specific. So different applications require these kind of features. So as a result, you also get equal amount of performance, right? So this is a good example right there. This is for digital power conversion.
So this is just another way of looking at the evolution of the dsPIC.
Yes, in terms of performance now, right? So this is a 3-pole 3Z compensator example from the moment the ADC triggers to the PWM update. So from 2nd generation dsPIC33FJ, which took about 1.84 microsecond for overall latency, the dsPIC33A core is down to 133 nanosecond roughly. So it's more than 10x improvement over, I don't know, 4 generations.
It's an order of magnitude.
Yep, exactly.
So what are some key features that make the dsPIC33A stand out?
That's another great question. So there are multiple things. If you look at the screen now, so on the left side, everything is improvement on the CPU.
Okay.
And then if you look at the right side, it's all peripherals. So we already talked about 32-bit CPU and double precision floating point unit. So this combination of these two help not only with increasing the performance, but they also help with adopting the third-party tools or model-based design with ease for our customer because they tend to prefer 32-bit architecture more. And on top of that, the 32-bit, along with 32, the double precision floating point, which is IEEE 754-2019 compliant, you don't get overflows and underflows in your results, and you don't need to do a lot of variable scaling. That's a big thing, right? It reduces the software error for any developer. So on top of that, we also did improvements on the DSP engine. The DSP engine of this 33A generation has two 72-bit accumulators, which improves the accuracy of the calculation and improves precision with faster math. And then we have 32-bit working register for, again, better performance, and then additional context switch register, which are very helpful during the interrupts. So again, lots of improvements on the CPU side. If you look at the right side, so there's lots of improvement on ADC. This is 12-bit ADC running at 40 megasamples per second. That's the conversion rate that you can achieve up to that level. And of course, you can oversample and get higher resolution than 12-bit as well. Again, for other analog peripherals like comparators are now 3 times faster than the previous generation. The response time is 5 nanoseconds. The op-amps are now 100 megahertz gain bandwidth product as opposed to 20, which was previous generation.
Yep.
And on top, and we also have very low offset, which is also user configurable. That means you get more accuracy.
So I see here root of trust, secure debug, a lot of security functions built in.
Yes. So there's lots of security features that have been added here because you want to make sure the firmware that your system is going to boot with is the authenticated one. The upgrade that you're getting is also authenticated. And also sometimes people try to sneak in through the debug mode. So that's why we have the secure debug as well. So lots of security features.
So I see functional safety, which you've mentioned before. You also mentioned AutoSAR. We've talked at length about security. Then I see dev tools. What are some kinds of dev tools and support does Microchip offer for the dsPIC33A?
I'm so glad that you asked that question. I brought some boards here.
Oh, okay.
Yeah. So actually, in terms of ecosystem, right, we have 4 prongs on that. So hardware tools, software, application firmware, and then there's the ecosystem, right? So if you look at this hardware board for general purpose application, if you look at this board, this is for a general purpose platform board for general purpose application, and then you have the dsPIC33A core based DIMM. These are sold separately. So if you want to evaluate this device, you just pop it in right here, and it plugs in, and then you can flash your program and evaluate the dsPIC33A for general purpose. Similarly, for motor control application, we have a motor control platform board, MCLV, 48 volt, 300 watt, and it has inverters. You can see all the 6 FET, so it can run a motor. And then you get a matching dual in-line module, or DIMM, we call it for short. This has the dsPIC33A core, and that, just like the previous one, it plugs in, and then you can start evaluating. Similar ecosystem exists for even digital power application too. So yeah, and in terms of software, there's a compiler.
I see the MPLab. Yep.
MPLab XCDSC already supports this device. Then lots of support we are adding for model-based design, for motor control first, and then we eventually will continue to add it for digital power conversion and sensor application. And then last but not least is the functional safety support, because you need lots of documentation and safety library. So we'll be adding those capabilities as well to support the dsPIC33A. So lots of ecosystem.
Yeah, so we're hearing that it's a hybrid model. It's kind of a best of both worlds. We see that we have a robust ecosystem around it. It really excels in very specific applications where you need performance with efficiency. So let's think about predictions now. What does the future hold for the dsPIC33A?
So based on the feedback we have received after the launch, everyone is very excited about it. And I think for real-time control applications, the future is really, really bright for dsPIC33A core family, especially with the 32-bit CPU, which runs at 200 megahertz, and double precision floating point unit, which not only helps enhance the performance, but also makes it easier for our customers to adopt the model-based design, right? So it's a very, very big jump for us. And then all the improvements that we did on the analog peripherals, that will help our customers achieve higher levels of accuracy and precision in their control loop. So if you talk about real-time control application, I think the future is really bright for dsPIC33A. It's a very formidable device.
Yeah, I see seamless adoption and low latency. Those are buzzwords that I think a lot of our audience is going to be very interested in.
Awesome. Thank you.
With that, let's get over to Aaliyah and see what kinds of questions we got coming from the interwebs. Aaliyah?
All right. First question is from Bharath on LinkedIn. Since I am pursuing in depth about embedded systems microcontrollers, how will these real-time systems be useful in this field from your view?
For what application again? Can you repeat that?
For real-time systems be useful in this field from your view?
Okay. For real-time control use, of course, this device already has capability in terms of analog peripherals. So if you're talking to analog world, you can do fast measurement with that. And then you have the compute capability with the 32-bit application. So if you're using this for real-time control application with the help of this analog peripherals and the 32-bit architecture, you can easily adopt it irrespective of whether you're using it for model-based design approach. I don't know if you're using model-based design or not, or you are trying to develop it on your own. We have support for both of these approaches. So for anything that you need, specific needs that you have, you can always reach out to us and we'll be very, very, very happy to help you.
Perfect, thank you. Let's go on with this question from Alan. Will code developed for dsPIC33C devices, as an example of legacy code, run directly on a dsPIC33A device? And is there a migration tool or wizard?
Very good question. So there is definitely a migration path. So dsPIC33C core is actually a 16-bit, and all the previous generation are 16-bit. And then dsPIC33A core is basically a 32-bit CPU. So there is, of course, no direct way you can convert it. So, but there's a migration path. So, for example, assembly code written for that C core may not directly always run on the dsPIC33A core. But if you have a C core device with C code on it, there's a migration path with the help of the registers that you need to update. So the compiler that you see, you have registers and peripherals. The look and feel for all the dsPIC DSCs are similar. So it will just flag the registers that you need to update once you compile it, and you make those updates, and then you can retarget that for dsPIC33A core. And on top of that, there's a complete migration guide that we have released. And with the help of that, you go step-by-step instruction on how to migrate your code to the dsPIC33A core.
That's good that they don't have to start over.
Yep, definitely.
Thank you. Here's another LinkedIn question for you. Can the device execute from RAM, or is execution limited to flash only?
So actually this device can execute from RAM, but due to addressing, there is one extra cycle, which is a trade-off. But it can execute from the RAM, and it is very important, especially for booting and programming. So yeah, this feature is there in this device.
Thanks, Pramit. This question is from YouTube. What are the key applications of DSCs in electric vehicles?
Ooh, electric vehicles.
Ooh, so that's a very interesting topic. So in terms of electric vehicles, there are lots and lots of applications, right? We talked about motors, like anywhere between 40 to 100 motors. So there's pumps, fans, compressor, lots of places where it goes for motor control applications. And now if you look at inside the cabin, there's touch modules. So you need to have very robust touch capabilities because you want to detect the touch even if you are wearing gloves in the winter. And also on the steering wheels, hands-on and hands-off detection. So for that, we see a lot of applications there. Then we talked about sensors. There are a bunch of sensors in EVs, right? Current sensor, temperature sensor, pressure for tire pressure. All those things have to be embedded and interfaced together. So there's that application. And then if you look at the charging side, charging the electric vehicle, there's onboard charger, which comprises of a PFC and a DC-DC converter. So you can use that. dsPIC DSCs find a home there as well. So yeah, lots and lots of applications for the electric vehicles.
Perfect. Thank you. Here is another question from Motion on LinkedIn. What do you suggest for learning DSP fundamentals?
Oh, so there are lots of ways for you to learn about dsPIC DSCs, I would say. We have some technical papers which are online, and then there are different app notes if you want to deeper into the application specific, like for motor control or digital power. We have several app notes with demo codes on it, and then if you really want to try it out on your hardware, you can always use these boards, and we have demo code integrated into this, and that way you can try it out after you learn. And of course, there's another way. There's something called as Microchip University.
Mm-hmm.
You can sign up for that course and learn on your own time. And then if you have, of course, further questions, you're always free to reach out to us, and then we can clarify it.
Speaks to that ecosystem you were talking about.
Exactly, exactly.
All right, we can do one more question. The last question is, where can I find code examples?
Okay, so there are lots of places to find code example. I touched upon the application note. So if you have, all application note have codes, sample codes there. And then you can find that on our website. If you look for application notes, that's one way to find it. The another way to find it is if you go Microchip Discover. There are bunch of sample codes for various applications. So there you can find it for motor control, digital power applications, sensors, and lots of different types of examples are there. Even for model-based design, MATLAB-based ones, so you can find it there to the multiple projects. So yeah, and if you need help with anything specific, you can always reach out to us too.
Microchip Discover is something I think we'll be talking about more in the future.
Yeah, awesome, sounds good.
Perfect. Thank you, Pramit. Thank you for answering our audience questions. And for our audience out there, if you have additional questions or comments, please email us at livestream@microchip.com after this broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Dana.
Thanks, Aaliyah. Well, Pramit, that was worth the coffee.
Yeah.
I want to extend a big thank you to our special guest for sharing his knowledge and passion with us today. It's conversations like these that remind us of the endless possibilities empowering your innovation in the world of embedded control and processing. If today's topic has sparked your interest and you'd like to learn more, I encourage you to visit our website at microchip.com, where you'll find a wealth of information and resources that dive deeper into the world of microchip technology. If you'd like more Coffee Break, head over to microchip.com/coffee break, click on the subscribe button to get updates for all things Coffee Break, and be on the lookout for upcoming episodes for season 14 of Coffee Break. Thank you for joining us here for season 13 of Coffee Break as we bring it to a close. If you like the show, we invite you to share Coffee Break with a friend or colleague. We'd love to have them join our community. The Coffee Break team is getting to work on season 14, and we'll have a sneak peek of those topics very soon. However, at this time, I'd like to acknowledge the amazing team behind the scenes here at Coffee Break. You may have noticed them in the pre-show feed, but what you don't know is we cannot do this show without them. So in no particular order, I'd like to thank Dave, Matthew, Tim, Jackson, Claudia, Maggie, Nicole, Michelle, Annette, Lisa, Megan, Sherlyn, Amanda, Diana, Marcy, Susan, Michael, and my superstar host, Aaliyah. Special thanks go out to all of our subject matter experts in front of and behind the camera, but most of all, thanks to you, our audience. We are here for and because of you. We appreciate you tuning into our show, and we hope to see you in a few months when we roll out season 14. Until then, stay curious, stay creative, stay caffeinated.